All right, so good afternoon. Our topic for today is analysis of bipolar amplifiers. Again, I'm Sir Febus from the School of Electrical, Electronics, and Computer Engineering of Mapua University. So regarding the analysis of amplifier, so every amplifier circuit will have a DC supply. So unang requirement yan. No? So it needs a biasing circuit to properly turn on the device, the transistor. So for amplifier application, transistor, bipolar transistor must operate in the active condition. Okay? So the base and emitter junction must be forward biased, while the base and collector junction must be reversed biased. So to provide the proper biasing requirements, we need the DC supply. In bipolar circuit, this is the supply VCC. And then, after establishing the operating mode, we can now connect an AC input. So we can now connect the AC input. So this would be the input signal of the amplifier. So essentially, in every amplifier circuit, we have two types of signals. You have a DC supply and an AC input. Then it will pass through the amplifier, and on the output, we will have the combination of DC and AC output. Now, knowing that you have two types of voltage sources, we can apply the analysis in our circuit called superposition theorem, wherein we are going to use DC supply only. So that would be the first step. So we can call it as the large signal analysis or the DC analysis. So in this case, we are going to use the DC supply only, and we are going to turn off the AC input. All right? And under this, we can determine the operating point, saturation point, as well as the cutoff point. Then, after knowing the effect of the DC supply, we can do another step, number 2, that is performing the small signal analysis or the AC analysis. So in this case, we are going to use the AC input only. And this time, we are going to turn off the DC supply. So using this step, we can determine the amplifier resistances. We can determine the input resistance and the output resistance. And we can also calculate the amplifications. We can have the voltage gain, current gain, and the power gain. And also, we can determine the frequency response. We can know the lower cutoff frequency, higher cutoff frequency, and the bandwidth or the frequency range of our amplifier. Then after knowing the effect of the AC input, the last step would be to combine the DC analysis and the AC results of the AC analysis. Okay, so is it clear so far? Please confirm.
Yes po, sir.
Yes po.
Yes po, sir.
All right, sige, thank you. Okay, let's go back sa slide natin, continuing. So here is an example of our common-emitter amplifier circuit, denoted by the input voltage connected at the base terminal, and we have a load resistor connected at the collector. So when you have an amplifier circuit where input is connected at base and the output is taken from the collector, that makes it a common emitter amplifier. So the emitter terminal will serve as the common terminal to the input and output terminals. So this is just one example of common-emitter amplifier circuit. So ang pinaka-indicator nun, check whether the input is positioned at the base and check whether the output is attached to the collector. So for our analysis of bipolar amplifier, we have the AC input, then we have the DC supply. Again, we are going to apply the superposition theorem. The first step is the large signal DC analysis. So you are going to use the DC supply only and turn off the AC input, and we are going to consider the capacitors as open circuit. So in this example, we have capacitor C1 and capacitor C2. These are what we call coupling capacitors. It connects the AC signal. So for example, the input coupling capacitor C1 connects the AC input to the base terminal, while the output coupling capacitor C2 connects the AC signal from the collector to the load resistor. All right? And another capacitor in the circuit is C3. This is what we call bypass capacitor. It connects the emitter terminal directly connected to ground. So when there is an AC input, capacitor C3 will behave like a short circuit. So that would connect the emitter to ground. But for our DC analysis, all of the capacitors will be considered as open circuit. So when there is a DC supply, the frequency is equal to 0 Hertz. Therefore, the capacitive reactance or the equivalent resistance of the capacitor is equivalent to infinity, or the capacitor will behave like an open circuit. Okay, so yan yung mga assumptions. Then on the next step, for the small signal AC analysis, we are now going to use the AC input only, and we are going to turn off the DC supply. And this time, we are going to consider the capacitors as shorted. So when there is a frequency more than or greater than 0 Hertz, the capacitive reactance will become very, very low. The ideal assumption, it will be almost equal to 0 ohm, such that capacitors can be treated as short circuits. Okay? And then the final step, again, we are going to combine the results of DC and AC analysis. Again, please confirm kung nakakasunod.
And follow
Yes
po,
po, sir.
Okay, so far, nakakasunod. Okay, thank you. Okay, let's continue. So let's now start with our DC analysis. Let us determine the equivalent DC circuit. So we are going to use the DC supply, and we are going to turn off the AC input. So in circuit analysis, to turn off the AC input or a voltage source in this example, to set Vin equal to 0, we are going to short the voltage source. So sa circuit analysis natin gagawin yon, no? So effectively, the input node will now be connected to ground, and the input voltage will be equal to 0. Then, consider all capacitors as open circuit. So when coupling capacitor C1 becomes open circuit, the input is no longer connected to the base terminal. When output coupling capacitor C2 becomes open circuit, the load resistor is no longer connected to the collector terminal. And when bypass capacitor C3 is open, then the emitter terminal is no longer connected to ground. And what we can see is what will remain in our DC analysis would be the bias circuit. So you'll have the supply, base resistor RB, collector resistor RC, NPN transistor Q1 and the emitter resistor RE. So the equivalent circuit for our DC analysis would be the bias circuit. Okay, again, is this clear? Saan ang galing yung equivalent circuit?
Clear po, sir.
Yes.
All right, thank you. So continuing on the DC analysis of the common-emitter amplifier circuit. So since this is a common-emitter amplifier, the input is base. So base current will serve as the input DC current. Base voltage is the input DC voltage, while collector current will be the output DC current, and the collector voltage, so that is the voltage from collector to ground. The collector voltage will serve as the output DC voltage. And for transistor Q1, VBE or the base emitter voltage is the input voltage of transistor. So pag ang tanong, determine the input voltage of amplifier, ang sagot doon yung VB, base voltage. But if the question is determine the input voltage of transistor, then you have to provide the value of VBE. Okay? And as for the output voltage of transistor, that will be the collector emitter voltage. Okay? Now, for the DC analysis, first step is we are going to assume the active mode of operation. Again, when we say active mode, we are going to assume that transistor Q1 is properly turned on, where base emitter junction is forward biased, while base collector junction is reversed biased. So we are going to assume that Q1 is in the active mode. So what we can determine is know the operating point or Q point. So we can determine the transistor interterminal voltages. We can calculate the VBE and the VCE. Again, VBE is the input voltage of transistor. VCE is the output voltage of transistor. Then you have IB, IC, and IE. Those are the transistor currents. For the common emitter, collector current is the output current, while base current is the input current. Then we can also determine the transistor terminal voltages. So base voltage is the voltage from base to ground. Emitter voltage is the voltage from emitter to ground. And lastly, collector voltage is the voltage from collector to ground. So for the common emitter amplifier, base voltage is the input voltage, while collector voltage is the output voltage. Okay, please confirm kung nasusundan.
Yes po, sir.
Sundan po, sir.
All right, thank you. So continuing on the active mode of operation. So normally, to determine the circuit parameters, so lahat nung IB, IC, IE, as well as VBE, VCE, and even base voltage, collector voltage, and emitter voltage. So usually, the first step is to use the transistor model. So Q1, the NPN Q1, follows these characteristics. No? The collector current is equal to the saturation current multiplied by the exponential of VBE over VT, wherein IS and VT are device parameters. So normally provided yan, no? Those are given parameters. The only unknown parameters would be VBE and the collector current. So we need to determine the actual VBE in the circuit as well as the operating or the actual collector current. So you have two unknowns, one equation, so we'll be needing another equation. So the other equation can be taken from the input loop. But before that, we have other equation in terms of collector current in terms of the base current. So you have a multiplier beta, which is the current gain. And IE is IC plus IB. So we can also express IE in terms of the collector current. Okay? Multiplied by beta plus 1 over beta. So again, from the equation 1, you have two unknowns. So we'll need another equation. So we can do a voltage loop dito. Alright, so what would be the equation? Tingnan yung circuit. Alright, somebody, ano yung equation natin dito? So that would be VCC minus voltage drop minus IBRB and then minus VBE and then minus IERE. All right, so input voltage equation would be VCC minus IBRB minus VBE and then minus IERE equal to 0. Then we can express base current as well as the emitter current in terms of the collector current, okay, using the beta parameter. So you have another equation for the collector current in terms of, again, VBE. So VCC, beta, RB, and RE are given parameters. So unknowns would be VBE and IC. Then use your algebra and we will be able to solve for the DC operating parameters VBE and IC. Alright, nasundan ba?
Yes, po, sir.
Alright, thank you. Then another way of doing the active mode of operation is if we include the early effect. So itong nauna, this is ignoring or neglecting the early effect. Alright? So wala yung VCE na component. But if we consider the early effect, this will be the model or equation for the transistor. So you have IC equal to IS times exponential of VB over VT, all multiplied by 1 plus VCE over VA, where VA is the early voltage. Okay, nasundan ba?
Yes, po, sir.
All right. Now, we can say ignore the early effect when VA is equal to infinity. So when VA is very, very high, then this becomes 1 plus 0. So we will have the simplified model. So in the previous equation, this is where VA is equal to infinity. Ito yung equation natin. Okay? Now considering the early effect, this will be the model. So in this equation 1, we will now have three unknowns. We need to determine collector current, base emitter voltage, as well as the collector emitter voltage. So we will be needing three equations to determine the three unknowns, with the assumption that IS, thermal voltage, and the early voltage are given in the problem, okay, in the circuit. So the first equation can be coming from the input voltage. So again, that would be VCC minus IBRB minus VBE and then minus IERE. Then we can express IB and IE in terms of collector current and current gain beta. And then another equation, we can derive the voltage equation along the output circuit. So this would be VCC minus ICRC minus VCE and then minus IERE. So at output, the voltage loop would be this, VCC minus ICRC minus VCE and then minus IERE. Then again, we can express IE in terms of IC. So from equations 1, 2, and 3, we use these three equations to determine VBE, IC, and VCE. So all we need is to use our algebra equations. Okay, nasundan ba? Please confirm.
Yes po, sir.
All right, thank you. Then after getting the operating voltages and operating currents, so at this point, you should be able to know the operating or the actual VBE, transistor currents IC, IE, and IB, as well as the voltage VCE. Then using this, we can verify whether the transistor is actually operating in the active mode. So when we do the analysis, we assume that Q1 is in the active mode. So yun ang assumption mo, no, na umaandar yung Q1. But after getting the operating parameters, we can double check whether Q1 is actually in the active mode, no? If it is really in the active mode. So dalawang magiging possible answers diyan, no? We can verify whether Q1 is in the active or whether Q1 is actually in the saturation mode. Yun yung possible answers na makikita natin dito. Okay? So to do that, we need to determine the operating point terminal voltages. We can get the emitter voltage. So from the circuit, we can see that emitter voltage is the voltage drop across resistor RE. So emitter voltage is just the current multiplied by the resistor. So VE is IE times RE. And then we can also calculate for the base voltage. We can do a voltage loop. So base voltage equals VVE plus the emitter voltage. So yan yung equation natin. And we can also determine the collector voltage from the collector to ground. So we can use a voltage loop from the power supply, VCC minus ICRC, and then minus collector voltage equal to 0. So pwedeng yun ang gamitin. Or we can see that the collector voltage is in parallel with VCE plus VE. Right? Nasundan ba dun sa circuit? Please confirm.
Yes, sir.
Okay? And then after knowing the transistor terminal voltages, we can now determine the operating mode. For the NPN, for it to be in the active mode, the collector voltage must be greater than the base voltage, and the base voltage must be more than the emitter voltage. So for example, let's say ito yung transistor, no? If for example, collector voltage is 5 volts, and then base voltage, let's say, is 6 volts, and then emitter voltage, let's say, is 4 volts. Given these terminal voltages, what is the operating mode of the transistor? Alright, sir, paano i-analyze yun? You have the base and emitter. We can see that ito yung base. Then here is the emitter terminal. We can see that the base voltage is higher than the emitter voltage. So base voltage is more positive or higher potential compared with the emitter. Alright? So ang polarity niya would be plus and minus. And what we have here is an NPN transistor. So N-type, base is P-type, emitter is N-type. So that means in the base emitter junction, positive voltage is connected to P-type, negative voltage connected on the N-type. Therefore, base emitter junction is forward biased. Alright, nasundan ba?
Yes po, sir. Yes po, sir.
All right, thank you. While for the base and collector junction, again, base is higher voltage compared to the collector. All right, so the polarity would be plus on the positive on the base, negative on the collector. So that means negative connected on the N-type, positive on the P-type. So that means base collector junction is also forward biased. And when the two junctions are forward biased, then we can say that this transistor actually operates in the saturation mode. All right, naintindihan ba? Please confirm.
Yes po, sir.
Yes, sir.
All right, thank you.
Sir,
Okay, yes.
either active mode or saturation mode lang po yung pwede.
Pag circuit, usually it is either active or saturation. But if you have any given circuit problem, ang possible answers mo doon apat. Pwedeng active, saturation, cut-off, or yung reverse active.
Okay po, sir. Thank you po.
Okay. Thank you. So you have to recall the biasing condition of base emitter junction and base collector junction for those operating conditions. Okay? Then, after knowing the active or the operating mode, we can also verify the saturation mode. So what do you mean by saturation? Saturation describes the condition wherein the transistor has already reached the maximum current or the maximum voltage. So normally it is the maximum current if we are referring to the transistor. So saturation mode, again, is the operating condition where the transistor has already reached the maximum output current. So ibig sabihin, kahit lakihan mo pa yung input current, the output current will no longer increase. Kasi na-reach mo na yung maximum. Alright? So to know how much is that maximum output current, we are going to apply the saturation mode. So to do that, we are going to get the voltage loop at the output circuit. So at the output, the voltage loop would be VCC minus ICRC minus VCE and then minus IERE. And then under saturation condition, the base emitter is forward biased as well as the base collector junction is also forward biased. Ideally, we can say that Q1 is shorted. So the collector and the emitter are ideally connected. So they are ideally shorted. So that makes the voltage from collector to emitter equal to 0 volt. All right, so at saturation, voltage drop between collector and emitter equals 0 volt. And since they are shorted, the collector current will go out to the emitter. So collector current is the same with the emitter current. Okay? And then substitute that to this equation. So BCE is 0. IE is also IC. Then we can derive or arrive at the collector current during saturation. Again, this is the maximum possible collector current. And it is equal to VCC divided by the total of the bias resistors at the output. So you have VCC divided by the total of RC and RE. Okay, please confirm if you follow.
Yes po.
Yes, sir.
All right, thank you. Now for the cutoff mode, again, we are going to use the voltage at the output. And we are going to apply the cutoff condition. In the active or in the cutoff operation, base emitter junction is reversed bias and the base collector junction is also reverse bias. When you have reverse bias, the internal resistance becomes very, very high. And so ideally, we can say that transistor Q1 will behave like an open circuit. The collector terminal is open circuit with respect to the emitter. And actually, even the base terminal is open circuit. So with this, the transistor currents during cutoff are considered zero. Okay, collector current is zero, emitter current is also zero, and even the base current is also zero. And if you substitute IC equal to zero, emitter current also equal to zero, then VCE during cutoff equals VCC. So that would be the voltage drop between the collector and the emitter. Okay? Can you follow? Please confirm.
Yes po. Yes po, sir.
Yes, po.
Okay, thank you. Let's continue. So by knowing the operating points, we can again verify the operating mode. So far we have two methods to determine the operating mode. Method 1 is by getting the terminal voltages and compare them whether we produce the forward reverse on the base emitter and base collector junctions. And based on the biasing of the two junctions, you can clearly know whether the transistor is in the active mode or in the saturation mode or in the cutoff or reverse active. Another method, this is the second method. We can know the operating mode by comparing the operating points with the saturation point and the cutoff point. So for example, in the collector current, we can plot the collector current at cutoff. So IC cutoff is 0. If you get a collector current equal to 0 or you calculated a collector current that is negative, it means that the actual operating mode of the transistor is cut off. Okay? And the maximum possible collector current is IC sat. So when you calculate the circuit, when you analyze and solve the circuit, and get a collector current that is equal to IC sat or even above or higher than IC sat, then you can state that the transistor is actually in the saturation operation. Okay? But if the operating IC, so denoted by ICQ, so Q means quiescent or operating point. So when the calculated operating collector current is within the saturation and the cutoff, then the transistor is in the active mode of operation. Okay, is that clear? Please confirm.
Yes po, sir.
Yes po, sir.
Yes, po,
All right.
sir.
Thank you. Then we can do the same for the VCE, but take note, you have the opposite, no? For collector current, ICO is 0. For the VCE voltage, VCE sat is the 0 value, and the maximum possible voltage is the VCE cutoff. So again, when the operating VCE or the Q point is a value within the cutoff point and the saturation point, then we can say the transistor is in the active mode of operation. Now, after knowing the operating points as well as the saturation and the cutoff points, we can determine the output current swing of transistor. So for the collector current, again, IC cutoff is equal to 0. Then the IC saturation is the maximum possible collector current. And you have the operating collector current denoted by ICQ. The difference between IC sat and the ICQ, that will give us the positive output current swing. While the difference between ICQ and IC cutoff, this will give us the negative output current swing. So the output swing will tell us how much of the output signal how much output we can have on the amplifier circuit. So for example, the output signal is a sine wave. The positive output swing will describe how much will be the positive half cycle, the amplitude of the positive half cycle. And the negative output swing will give us how much will be the negative output swing. So the ideal position of the ICQ is at the midpoint between IC SAT and ICQ so that we can have the maximum positive output swing as well as the maximum negative output swing. Is this clear?
Yes,
Yes, sir.
po.
All right, thank you. Sir, what will happen if let's say yung ICQ medyo malapit sa IC SAT or closer to the IC cutoff? So you have two possibilities, no? So we said that the ideal position is at the middle. But in case, based from the bias circuit, let's say the ICQ becomes closer to the IC SAT, then there is a probability that the positive half cycle of the signal will be distorted or clipped. So yun yung danger natin doon, no? So pwede magkaroon ng distortion on the positive half cycles. While when the ICQ is closer to the cutoff, there is a tendency of distortion on the negative half cycles. Naintindihan ba? Please confirm.
Yes po, sir.
Yes, po.
So later on sa lab natin, we will have a design of amplifier and you can observe what happens kapag merong distortion, no? So you are going to record your voice and using the LT Spice, we can convert that voice into input voltage. All right? Then passing through the amplifier, lalaki yung signal natin, no? And if there is distortion, yung output voltage converted back to audio file, so pwede mong marinig yung input tsaka yung output voice. Then kapag may distortion, you can notice na parang ano yan, may hangin or may noise yung output natin, no? So not necessarily na nakiklip talaga, no, nawawala yung audio, but more of para siyang noisy. Parang umuulan sa paligid mo or you have like electric fan sa background. Ganun yung mangyayari dyan. So when the ICQ is near the IC saturation, the positive swing of the output is bound for distortion. While when the ICQ is near the IC cutoff, the negative swing of output will be prone to the distortion. Then we can also have in terms of voltage. So again, 0 is when VCE is at saturation. Maximum is BCE cutoff. And BCE operating point ideally should be at the middle to have the maximum positive output swing as well as the maximum negative output swing. So in case the Q point becomes closer to cutoff or on the saturation point, in terms of voltage, when the operating VCE is near the BCE cutoff, the positive swing of the output is bound for distortion. While when the BCEQ is near the BCE SAT, the negative swing of output is prone to distortion. All right? So is this clear so far?
Yes, sir.
Yes po, sir.
Yes po.
All right, thank you. Okay. So let's continue on the small signal analysis of Common-Emitter amplifier. So again, this is the example of Common-Emitter amplifier. So to do the small signal analysis, we are going to use so that means the VCC will be directly connected to ground. So this kind of circuit notation means that we actually have a voltage source plus VCC. So that means on that node, you have the positive terminal and the negative terminal will be connected to the ground. And the voltage is equal to the VCC. So when we turn off the DC supply, so since this is a voltage source, we are going to short the voltage source to set the VCC equal to 0 volt. And when we do that, this node will be connected to ground. So effectively grounded na to. Alright, nasundan ba?
Yes, sir.
Alright, so yun yung ibig sabihin nun. And we are going to consider the capacitors as shorted. So capacitor 1 will be shorted. Coupling capacitor C2 is also shorted. And bypass capacitor C3 will be treated as shorted. And when we apply those conditions, the equivalent circuit will now have, all right, take a look at this. The emitter terminal will now be directly connected to ground, or the emitter is now bypassed to ground. Then for base, take a look at the base terminal. Base terminal will now have base resistor RB connected between base and ground. And you have input voltage connected between base and ground. So when we draw the equivalent circuit, Vin will be connected in parallel with RB, and the two will be in parallel, connected between base and ground. And at the collector, we will now have RC, collector resistor connected between collector and ground. And RL, since C2 is already shorted, load resistor is connected to the collector. So from collector, you also have RL connected between collector and ground. Okay, nasundan ba yon?
Yes po.
All right, so this will now be the equivalent circuit. Sir, paano nangyari yan? This portion, to. If you notice, meron tayong label, no? You have the base terminal, emitter terminal, and the collector terminal. So all of the components here are the equivalent circuit of, this is just the transistor Q1. So from our small signal model of bipolar transistor, when we apply AC signal, the bipolar transistor behaves like a forward bias resistance between base and emitter terminal. So that is denoted by R pi. And it also behaves like a voltage-dependent current source between collector and emitter. So you have here the collector current equal to transconductance parameter GM times V pi, where V pi is the voltage between the base and the emitter. Right? And in parallel with RO or output resistance, so this would be the reverse bias resistance from the collector to the emitter. All right? So this is the equivalent circuit of bipolar transistor. So pag meron kang semiconductor device, for example, in a semicon industry, they will fabricate the bipolar transistor. And then they will apply actual voltage and measure, let's say, the resulting currents. So magkakaroon sila ng current voltage characteristics. And then they will think of equivalent circuit that will produce the same current voltage characteristics. So for the bipolar transistor, this is the equivalent circuit. Alright? So napag-isipan na nila yan, no? By using these components, this will simulate, this will imitate the actual behavior of bipolar transistor. Naintindihan ba?
Yes.
Or clarification, question? Nasusundan?
Yes, sir.
Alright, sige. So let me erase muna to. Okay, continue. So again, this is the transistor equivalent circuit. And on the base, or on the emitter muna ito, for the emitter will be directly connected to ground. Then for base, we'll have, ito yung base natin, we'll have the RB in parallel with Vin. And for the collector, we'll have the RC in parallel with RL. Okay, so dun galing yung equivalent circuit natin. Okay, and then after getting the equivalent circuit, we can now determine the equivalent resistance. Alright, so let's say determine the resistances, input and output resistances of common-emitter amplifier. So from the equivalent circuit, starting from this point, nandito yung input node, no? This would be the start of the amplifier circuit. Hanggang sa RC, nandito yung output node. So yung Vin is not part of the amplifier circuit. Likewise, yung RL natin is also not part of the amplifier circuit. Okay? So if we measure the resistance between these nodes, between base and ground, we can get the input resistance. And if we measure the resistance between collector and ground, we'll be able to determine the output resistance. Okay? So, ganyan yan. But, when you do the measurements, ito yung reminder. For the input resistance, so this is the amplifier circuit. If we want to determine the input resistance, we are going to remove the AC input voltage and apply a known voltage source Vx. So maglagay ka ng known voltage source and measure the resulting Ix. So based on the Vx and Ix, we can calculate the input resistance. So Rin would be Vx divided by Ix. And there is a condition. When measuring the input resistance, make sure that the output terminals are open circuit. So wag ka maglagay ng load. Okay? So this is the equivalent circuit. Again, we connect a known voltage source, Vx, and then measure the resulting Ix. Then from there, we can get Rin. So again, Rin equals, by using Ohm's law, resistance is equal to voltage divided by current. So you have Vx over Ix. All right? So again, the output must be open circuit. Now look at the schematic diagram. What is Vx? So you can do a voltage loop. So that would be plus Vx minus V pi, balik doon, equal to 0. Nakita ba? Please confirm.
Yes po.
Yes.
All right. So we can replace Vx in terms of V pi. We use the symbol pi na lang, no? Alright, then divided by Ix. From the circuit, what is Ix? Ix is equal to, so we'll have here base current. And we can label the current here, let's say, as I1. So Ix is equal to base current plus I1. Right?
Yes, sir.
All right. And for base current, what is base current? You have voltage and resistance. So base current is V pi divided by R pi. While yung I1, what is the voltage across RB? If you look at the schematic diagram, these two nodes are connected together. The other node is grounded. The other node is grounded. That means RB is actually in parallel with R pi. So the voltage across RB is also V pi. So again, Ix is IB plus I1, where IB is V pi over R pi, and I1 is equal to V pi over RB. So pwede nating isulat yun dito, no? So Ix is IB, and it is equal to V pi over R pi. All right, plus I1, where I1 is, again, V pi over RB. So from the equation, we can cancel out yung V pi. So the input resistance now equals 1 over R pi plus 1 over RB. Or reciprocal of reciprocals, no? So lumalabas, R in is actually R pi in parallel with RB. All right, can you follow?
Yes po.
Yes po,
Yes
sir.
po.
All right. Or actually, pag tinignan mo yung circuit, tingnan mo rito, ang may kita mo dyan yung RB in parallel with R pi. Since yung nodes nila connected eh. Okay, is that clear?
Yes po, sir.
Yes, sir.
All right, thank you. Then how about the output resistance? If we want to determine the output resistance of Common-Emitter amplifier, we can apply the known voltage source at the output terminal and measure the resulting Ix. And then from there, we can calculate R out. So in this case, R out equals Vx over Ix. Then as for the input terminal, the requirement is we are going to short the input terminals. So pakitandaan yung requirements na yon, no? So for our equivalent circuit, at the output, we apply Vx and Ix, and we are going to determine R out. And as for the input, it is shorted. All right, is this clear?
Yes, sir.
Yes po, sir.
Now, by having the input shorted, it means that base is connected to ground. Agree?
Yes
Base
po.
becomes connected to ground. How about the emitter? Emitter is also connected to ground. So that means the voltage V pi, yung both nodes are shorted or connected to ground. That means V pi is equal to 0 volt. So we don't have any input voltage source. And when V pi is 0 volt, then how much is the collector current? So IC is GM times V pi. GM times 0 volt, that makes collector current equal to 0 ampere. So that means the current source is effectively open circuit. So wala to bale, no? Tanggalin mo yan sa analysis natin. So what will remain are the collector resistor in parallel with the output resistance of transistor. So they are both connected to the collector. The other side, they are both connected to ground. So that means R out is equal to RO in parallel with the collector resistor. All right, can you follow?
Yes.
Yes po.
All right. Now, in case we have a condition, let's say the problem states that neglect the early effect. Again, what do you mean by neglect the early effect? It means that VA is equal to infinity. So R out will also be equal to infinity. So that makes the output resistance open circuit. So when this is open circuit, then R out, if we neglect the early effect, R out will just be equal to the collector bias resistor RC. All right. Nasundan ba? Please confirm.
Nasundan po.
All right. Thank you. And then, we can also determine the voltage gain. So what do you mean by voltage gain? Voltage gain is, let me change the color. All right. Voltage gain equals the ratio of the output voltage divided by the input voltage. So in this schematic diagram, the output voltage is across the load resistor. And the input voltage is this one, yung Vin. All right. Then for us to determine the voltage gain, what we can do is we can trace the flow of the voltage. So again, we have the common-emitter amplifier. So the input will be base. So that means the input voltage will be applied to the transistor as the base voltage. And again, as a common emitter, the output is the collector. So the base voltage eventually will become collector voltage. And then finally, the collector voltage will become output voltage. So based on this, we will have three segments. This will be the input side. Then from base to the collector, you have the transistor. And then from collector to load, we'll have the output circuit. All right? So using these three segments, we can also express the voltage gain as for the output circuit, voltage gain is output V out divided by input collector voltage. So you can write V out over collector voltage multiplied by voltage gain of transistor. That would be output collector voltage divided by the input base voltage. So you can write VC divided by the base voltage. All right? Then multiplied by, on the input circuit, you have output base voltage divided by the input Vin. So you can write multiplied by base voltage divided by the input voltage. All right? Nasundan ba? Please confirm.
Yes,
Yes
sir.
po.
All right. And you can double check. Kailangan mag-cancel out, no? VC canceled, BB canceled. So you will derive the overall equation, no? V out over V in. Okay? But syempre hindi natin ika-cancel out. Take a look at the output circuit. We can notice that V out is actually in parallel with the collector voltage. Tama? They have the same loads. They are both connected to the collector and connected to ground. So V out is in parallel with the collector voltage. So that means they have the same voltage level. So V out over VC will be equal to 1. So alam na agad natin yon. And on the input side, V in is also in parallel with the base voltage, having the same nodes. So they are both connected to base and both connected to ground. So V in is the same with VB. So that means the ratio of VB over V in is also equal to 1. So to solve for the voltage gain, we need to determine the collector voltage over the base voltage. All right. So take a look at the collector voltage. Collector voltage is the voltage drop across RC and RL. So you have the resistance. Now, how about what is the current flowing here? What is the current flowing here? So that would be, or possibly pwede nating i-trace pabalik dito, no? We can say that the collector voltage is across RC, RL, and actually yung R out nakaparallel din, no? They are connected to collector and ground. So you have 3 parallel resistors, and the current flowing through that parallel resistors is the negative of the collector current. Nasundan ba? So collector voltage can be written as negative IC. This is the current multiplied by the resistances. You have R out in parallel with RC, in parallel with RL. All right. So are you following?
Yes, sir.
Yes po, sir.
All right. Then how about the base voltage? If you look at the schematic, again, base voltage is in parallel with V pi. Tama ba? So base voltage is the same as V pi. V pi is between base and emitter. Emitter is grounded. Base voltage is between base and ground. So base voltage VB is the same as V pi. Sir, bakit mo in-express ng V pi? We can express IC in terms of V pi. So we can write IC in terms of transconductance GM times V pi. And afterwards, we can cancel out V pi with another V pi. So therefore, the voltage gain is now equal to ano ilalagay natin? Voltage gain is negative of transconductance GM multiplied by R out parallel with RC, then parallel with RL. So just compute for GM using this. you have the operating collector current divided by the thermal voltage. And you can get the equivalent voltage gain. All right? So, nasundan ba? Please confirm.
Yes
Sundan
po,
po.
sir.
All right. So, hanggang dito lang muna tayo for this afternoon. Any question?
None naman po, sir.
Wala po.
None po, sir.
All right. Thank you.